Hi everyone, welcome to Chapter 2, The Chemical Foundation of Life. So your learning objectives for this chapter is to define matter, define element and atom, distinguish between protons, neutrons, and electrons, and describe their relationships to an element's atomic number and atomic mass, differentiate ionic, covalent, and hydrogen bonds, differentiate polar and nonpolar covalent bonds, and define valence number and model the valence configuration of various atoms. Most of what you're going to see here is by way of review. Most of the information here, at least in the early part of Chapter 2, you've been exposed to in life science or 10th grade biology. So this should be a fairly good review for most of you. So when you hear the term biology, generally, most people think of plants and animals, rivers and streams, bacteria or viruses that make us sick, or anatomic structures like the heart, skeleton, your skin, your muscles. But biology is much more than the structures that you see and are very familiar with in the natural world. In fact, as I say here, everything that you see, smell, hear, taste, and feel, everything that stimulates the special senses in the natural world is a product of a series, and sometimes it's a huge series, thousands even, of interconnected chemical reactions. There's a subdiscipline of biology, you probably have heard of it, called biochemistry, that is devoted to the study of just those chemical reactions. As an undergraduate, I took a whole semester course in biochemistry. It's a large discipline. Some biochemical reactions are extremely involved, but you don't have to worry about that. We're just going to take a superficial look at some of those very basic chemical reactions as we enter into Chapter 2, the chemical foundation of life. So the first thought here is, what is matter? And again, you learned this probably in 3rd grade. Matter is anything that has mass and occupies space. It may be either living, like this black mountain lion or black puma or black cougar, or whichever term you want to use there, that you see here on the left, and this Rolex watch on the right. My desk here, my cell phone, the computer that you're using to watch this presentation, my little kitty, Princesa Dulce, who just left the room, living versus non-living, anything that occupies space and has mass. That is matter. When we think of matter, we sort of automatically, I think, at least in my mind, automatically go to the periodic table of elements, because matter is made up of elements. And you do not have to learn the periodic table, right? That's chemistry class. But there are some things that we need to know about the periodic table with regard to a small group of very special atoms or elements that are very prevalent in biological systems. So an element, by definition, is a pure substance composed of a single type of atom. And so from the periodic table, we know elements like carbon and nitrogen, oxygen, helium, hydrogen. Element cannot be broken down into any other substance, okay? So examples of elements here that I have: hydrogen. By the way, in parentheses, you see the capital letter H. This is the chemical designation for the element hydrogen, capital H, capital C for carbon, capital O for oxygen, capital N for nitrogen. You see how that works. Some elements are designated with 2 letters. That's going to be a capital and lowercase letter, in this case HG for gold. That comes from the Latin, by the way. Silver is AU, iron is Fe. So an atom is the smallest unit of an element that has all the characteristics of that element. An element is the thing, gold or hydrogen. An atom is the physical representation of the thing, a gold atom or a hydrogen atom or a carbon atom. Okay, it's the smallest unit of an element that has all the characteristics of that element. Atoms, you've heard this before, are the basic building blocks of all matter, be it living or non-living. Everything is composed of atoms. And so structurally, an atom consists of a core. We call that the nucleus, and the core is made up of protons and neutrons. We'll differentiate them in a minute, surrounded by a cloud of electrons. Now, electrons orbit the nucleus like tiny planets orbiting the sun. And we'll see that in the illustration that I had to show you. Here's the basic atomic structure of a generic atom. We see the core here made up of protons and neutrons, protons in blue, neutrons in red here, and together they make up the core, which we call the nucleus. And traveling very fast around the nucleus in all different planes are these elements, subatomic elements that we call electrons. And I always describe the electron series of electrons traveling around as a cloud, because if you were able to look at this subatomically, it would be like a big blur. The electrons travel so fast, and they're all over. We just see this in 2 dimensions here, but the atom is a 3-dimensional structure, and the electrons just whip around the core, the nucleus, and they go so fast it's just like a blur, and so it looks like a cloud surrounding the nucleus. So subatomic particles include your protons, neutrons, and electrons. Remember that the nucleus, or the core, is composed of protons and neutrons. What's the difference? Protons have a positive electrical charge, right? That's the pro part of proton, has a positive electrical charge. Neutrons, by definition, are neutral. Therefore, they have 0 or no electrical charge. And on the flip side of the coin, from protons, we have electrons. Electrons orbit the nucleus, and they have a negative electrical charge. And by the way, and as we'll see, it's the chemical behavior of an atom is due to the number and configuration of electrons in that little cloud that orbits the nucleus. So in a normal occurrence, an electrically neutral atom, that's the normal situation. We're talking about the natural world here. And in the natural world, everything wants to be in balance or neutral. And so an electrically neutral atom has the same number of protons, positive charges, as the number of electrons, negative charges. So in the case of carbon, you have 6 protons, 6 positives, and a neutral atom of carbon therefore has 6 electrons or 6 negative charges flying around it in its little cloud. 6 positives plus 6 negatives equals 0, or an electrically neutral atom. So the positive charges and negative charges cancel each other out, so that the atom's net charge is 0. This is in the normal situation, in the balanced situation. So here we see a Bohr model, that's B-O-H-R. And so this shows you an atom and the relationship between electrons, protons, and neutrons as a 2-dimensional image. Remember that, and I can't stress this enough, that an atom is a three-dimensional structure. Okay, but we're just seeing it here in 2 dimensions. So here's the nucleus composed of your protons with their little positive charges and the neutrons with their zero charge, right? No electrical charge on neutrons, and they're neutral. And together they bind together to form what we call the nucleus. Now, traveling around extremely fast in various levels, various orbits, or energy levels, we'll look at both terms as we go along, are the electrons. Electrons have a negative charge. And so by definition, we have to have, in a neutral situation, we have to have the same number of protons as we do the number of electrons. So, if you look at this little model here, there's 1, 2, there's 3 hidden back there, there's 4 over there, 5, 6, 7 positive charges, so 7 protons. So therefore, we would expect to see 7 electrons. So we have 1, 2, 3, 4, 5, 6, and 7. And so we have a neutral atom here. Now you'll notice that the relative size of neutrons and protons are the same. There's a very little difference between the mass of a neutron and the mass of a proton. You'll notice in this Bohr model, the electrons are represented as little tiny blue dots, right? Little tiny blue circles. Look at the difference between the size of an electron and the size of a proton. Now, this is an illustration to demonstrate the point, but the point being, electrons are extremely small, and in fact, the mass or the weight, we call it the mass, of an atom is insignificantly affected by the mass of electrons, regardless of the number of electrons which are there. Okay? Well, I'll explain that a little bit more in detail in a second. All right? So atoms are defined by their atomic numbers. The atomic number then is the number of protons in the nucleus of an atom. So atomic, you'll always see this in the periodic table as an element is represented. You'll see the atomic number always there. It's the number of protons, the number of positive charges. The atomic mass then is equal to, now we're talking about the nucleus here, the core, so the atomic mass is equal to the masses of the protons and the neutrons together. As I said, roughly the same mass in a proton as in a neutron. So and they're bound together. And so the atomic mass of an atom is equal to the number of protons plus the number of neutrons. So in the case of an atom of carbon, you have 6 protons. That's going to be the atomic number. So the atomic number of carbon is 6. You're going to have an equal number of neutrons in the normal situation. So that means you're going to have 6 neutrons in the atomic mass. You just add them together. So 6 protons plus 6 neutrons equals an atomic mass of 12. So carbon has an atomic mass of 12. Now orbitals are the rotational paths that electrons travel around the nucleus, and they travel 3-dimensionally, okay? Not 2 dimensions like the Bohr diagram represents. Always remember, this is like a little ball, and the electrons travel around, and it's very fast. And if you could see this on a subatomic level, you would just see a blurred cloud. But there are in individual orbits, orbitals, or energy shells. And by the way, electrons can jump back and forth. I'll show you that in a second. They can jump back and forth between orbitals, and they do regularly. So electrons are maintained in their orbitals due to their attraction to the positively charged nucleus. Remember, electrons have a negative charge. Protons have a positive charge, and so therefore the nucleus has a positive charge, and the negatives electrons are attracted to the positive protons in the nucleus. Remember that opposites attract. All right, here we see more diagrams of several important biological elements, beginning here with hydrogen. Hydrogen has one proton in its nucleus. Notice that hydrogen does not have any neutrons, just one proton. So the atomic number of hydrogen is one proton, but also the atomic mass of hydrogen is 1. And so it has one proton, so therefore as a neutral element, it has to have one electron, right? So the -1, the +1 cancel out. Here we have a neutral atom of hydrogen. Here's carbon, and carbon is extremely important in organic systems, as we'll see as we go along. The nucleus, we have 6 protons and 6 neutrons. Therefore, we have an atomic mass of 12. And because we have 6 protons, positive charges, we would expect to see in the neutral situation 6 electrons. And there you can see 2 here in this first orbital, or energy shell, and 1, 2, 3, 4, plus 2 is 6 electrons. Here's nitrogen, 7 protons, 7 positive charges, 7 neutrons, atomic mass of 14, 7 protons, positive, we'd expect to see 7 electrons. There's 2 in the inner orbital, and 1, 2, 3, 4, 5 in the second orbital. Now, you should notice a pattern here, going from here to there. There are only 2 electrons in that first orbital, with nitrogen as well. And as we look at oxygen over here, look, 1, 2, only 2 electrons in that first orbital, or that first energy shell. We use those terms interchangeably, and I'll explain that more in detail later. But that first energy shell, that first orbital on any atom, can only contain a maximum of 2 electrons. And then you move out to the next energy shell, and that can contain a certain number. And then if the atom is big enough, you go to a third shell, and then you go to a fourth shell until all of the electrons are accounted for. So here's oxygen, 8 protons, 8 neutrons. All right, atomic mass of 16. 8 protons positive would yield 8 electrons. There's 2 in the first shell, and 1, 2, 3, 4, 5, 6 in the second shell. 6 plus 2 is 8. All right. So when we look at the periodic table, and you are not going to have to memorize the periodic table for sure, but there are some things that you want to be able to understand when looking at the periodic table with regard to those elements that are most important to biological systems. So it's not presented, all of the information here is not presented in every illustration of the periodic table. Depends on the source, but most of the information is here starting, you usually see it in a little box like this. Starting with the element's symbol. Right? In this case, capital H, I've already told you before, H stands for hydrogen. You can see the element's name down here. Element's name is not always there, but for our purposes, it will be. So capital H, hydrogen, the name of the capital H is the symbol, the name of the element is hydrogen. Now it has 1 proton. So this represents up here the atomic number. Remember, atomic number is the number of protons. So hydrogen has 1 proton. Put a little asterisk here to direct you down here. Hydrogen's nucleus has 1 proton and 0 neutrons. Okay, so only one proton. But regardless, whatever element you're looking at, that number up there is always going to be the atomic number or the number of protons. And so the atomic weight of hydrogen is 1, roughly 1.008. Some of that comes from the weight of the electrons, but as you can see, right, it amounts to 8/1000th of a Dalton for hydrogen. So it's for all intents and purposes, at least for our purposes here in general biology, the weight of, or the mass of the electrons is negligible, no matter how many are there. So roughly, hydrogen has an atomic mass. It says weight over here, but the better term is mass. Has an atomic mass of 1. And that's how you read the periodic table. So if we look at these elements here, there's carbon, important to biological systems, nitrogen, as is oxygen, sulfur, we'll see some chlorine along the way, not so much aluminum or gallium, but anyway, you get the idea. So here's carbon, atomic number 6, there's the name. We don't see the atomic mass here in this representation. There's nitrogen with its atomic number of 7. That means 7 protons, and so you know by definition that also means 7 neutrons. So we don't have to put the number of neutrons there because we know it's 7 is equal to the number of protons. Nor do we have to put the number of electrons there because we know that the number of electrons in a balanced atom has to be equal to the number of protons. So the atomic number is 6 in carbon, but we know, therefore, that there are 6 neutrons and 6 electrons as well. In case of nitrogen, 7 protons, that means 7 neutrons, an atomic mass of 14, and that also means 7 electrons. Here's oxygen with its 8, atomic number of 8, that means 8 protons, therefore 8 neutrons, and that gives it an atomic mass of 16, and we also know that there are 8 electrons in a neutral atom of oxygen. Okay, that's how that works. So quick review here, question, I'll give you a couple of seconds to think about. What is matter? And again, this is not a revelation, I think, for any of you. So what is matter? Anything that has mass and occupies space. Probably want to remember that definition. What is an element? Think about the periodic table, right? An element is a pure substance composed of a single type of atom. And so what is an atom? Would be the follow-up question. An atom is the smallest unit of an element that maintains the characteristics of the element. So as I said before, with regard to the periodic table, the element, carbon, hydrogen, helium, nitrogen, sulfur, the element is the idea, right, which is in the periodic table, is the idea of an element. The atom is the physical structure, the three-dimensional structure representing that element. If that makes any sense, I hope it does. Okay, so what is the atomic number? Well, the atomic number is the number of protons in the nucleus of an atom, right? And we know that protons have positive charges. So then what is the atomic mass? Well, we know that the atomic mass pertains to the nucleus of the atom where we have protons and neutrons. And so the atomic mass is the addition of protons and neutrons. In the case of carbon, 6 protons, 6 neutrons, we have an atomic mass of 12. So the mass of an atom's nucleus is the number of protons added to the number of neutrons. And what is an ion? I mentioned ion earlier, but I will next, but just kind of get you thinking, what is an ion? Well, remember that a neutral atom has the same number of protons as electrons. The positives and negatives have to balance out. But what if an atom does not have or has an unequal number of protons versus electrons? That is an ion. So an atom with an unequal number of electrons. So you might have 6 protons and 7 electrons. What's that all about, right? Call that an ion. So ions have a net chemical charge. We know that a neutral atom is neutral, right? It has a 0 electrical charge, but ions have an electrical charge. So ions are atoms with an unequal number of electrons. Number of electrons does not equal the number of protons. Therefore, an ion has a net electrical charge, either positive or negative. If you have one fewer electrons than you do protons, then we get a positive charge, right? One more plus. If you have one more electron than you do protons, then you have a net negative charge. We call those two things, we give them different names. And those names are cation. So cations have lost an electron and so have a net positive charge, right? So if you have 6 protons and 6 electrons, and you lose an electron, right? So you have 6 positives, 6 negatives, but you lose a negative, then you have 6 positives and 5 negatives, which means you have a net positive charge. So examples of cations in the natural world in biological systems are calcium, that's Ca, and we denote ions with the little electrical charge. In this case, it has a +1 charge. You just put plus there. Positive electrical charge. Here's sodium, that's Na, with its little +1 up there. And K is potassium with its little +1 up there. Now, on the flip side of that coin are the anions. Anions have gained an electron and thus have a net negative charge. And so examples here are chlorine with its little -1 up there, and oxygen with its little -1 up there. Okay, so cations have positive charges, anions have negative charges. All right, quick knowledge check to wrap this part of chapter 2 up. So given a single atom of potassium, the chemical symbol for potassium is K. Potassium is an atomic number of 19. That means that, think about it, we have atomic number, that's protons, so there are 19 protons in a single atom of potassium. Atomic mass is 39. Now, atomic mass is the number of protons plus the number of neutrons, right? So keep that in mind. And so the question is, which of the following statements is false? So let's look at these one at a time. A says potassium has 20 neutrons. Well, we know that the atomic mass is the number of protons plus the number of neutrons. We know the number of protons, that's the atomic number here. So 39, doing simple math, 39 minus 19 is 20. So one atom of potassium has 20 neutrons. So A is clearly correct. Okay? B says a single potassium atom has an electrical charge of +19. All right? So remember that in a balanced and neutral atom, in this case potassium, the number of protons, which is the atomic number 19, must equal the number of electrons. So we have 19 pluses and 19 negatives, and that gives us a potassium atom with a 0 charge. That's the normal situation. So a single potassium atom, it's implied here that we're talking about the neutral situation. It has an electrical charge of 19. Well, it's a neutral atom, so it has no electrical charge at all. So B is clearly false. C says potassium has 19 electrons. Well, how many electrons does potassium have? Well, potassium has an atomic number of 19. That's the number of protons. And in the neutral situation, the number of protons plus charges must equal the number of electrons, negative charges. So therefore, we can presume that potassium with 19 protons also has 19 electrons. So C is clearly true. D says a single potassium atom has an electrical charge of minus 20. Now here we're talking about, again, implied the neutral situation for potassium. So we have a negative electrical charge. So D is clearly false. E says both A and C are false. Well, we know that A is true and we know that C is true. So clearly E is false, right? Because two wrongs do not make a right. And F says both B and C are false. Well, we know that B is false, but we also know that C is true. So F is clearly false. Once again, two negatives don't make a positive. All right, don't be surprised if you see a question similar to this one on this week's quiz. And so you should be able to tease out the correct responses based on what you know about these definitions: atomic number, atomic mass, electrons and protons, etc. Okay. All right, that ends this segment of chapter 2, and we'll continue chapter 2. I'll do another situation, another presentation for you, and post it on Wednesday for chapter 2, which gets a little more in-depth now. Okay, but this gives you some basic information to get started on. All right, so there you have it, and I will see you next time.